Welcome to the second video in Unit 5, where we'll be discussing the mechanism of SNAc reactions. So just to remind you, the general SNAc reaction is shown here, where we have some kind of an acyl group and a Y group, which we know is going to function as a leaving group, as well as some kind of a nucleophile. For now, we'll treat the nucleophile as negatively charged, but the critical thing is that there's a lone pair here that we can use. And we know a couple of things about this reaction just by inspection, just looking at the structures of the products relative to the structures of the reactants. We know that we're going to be breaking the carbon Y bond, and we know that we're going to be forming the carbon nucleophile bond. And it looks like those are the only structural changes that happen overall. There could be other structural changes if there's multiple steps. We don't know about those yet. So what we need to do now is come up with some proposals about how this reaction could happen. One proposal is to take what we know about the SN2 reaction and apply it here, because it looks a little bit like that, right? We could just take the Y group and make it leave. We could bring nucleophile in all at once. It would look something like this. And that would be it, a single step. So I'll draw products for completeness. Certainly, this kind of a mechanism would explain all of the bonding changes. It would explain the CY bond breaking and the carbon nucleophile bond forming. And it would also show how we end up with a Y group that's gained a lone pair. Great. So another possibility is we could treat this more like an SN1 reaction. So we could take the same set of compounds and now do these structural changes in two separate steps. Rather than dealing with all of the bond changes at once, first we could dissociate the Y group. That would give us a carbocation, like this. Our Y, lone pair, negative charge, and our nucleophile, lone pair, negative charge. So this would be like a set of intermediate structures, and then the second step, the nucleophile could associate to the carbocation center. So again, this is by analogy to SN1. And we get the same set of products. All right, so those are both options. A third option would be to actually reverse the order of operations. So we would basically bond the nucleophile to the carbon first, and then in a second step, we would break the carbon Y bond. So we'll look at that proposal as well. So here, we'll redraw my compounds. I'm going to form a new nucleophile carbon bond. But I also know that the thing that I can really never do in any kind of a reaction that we would normally think of, certainly anything in like a typical organic chemistry context, we never go over the octet rule for second row elements. It's so destabilizing to do this that essentially no structures we observe ever have this kind of feature. That's not to say that you can't make it happen, it's just extremely unusual. But what we could also consider is whether it would be possible to actually break like a CO pi bond. We've seen things like this before, where pi bonds get broken to make room for new sigma bonds. When you learned about addition reactions back in OChem 1, you learned about this. So one possibility is, rather than going over the octet rule for carbon, we could essentially break the CO pi bond and put the electrons in that bond just on oxygen. And that might be okay because oxygen's so electronegative. We wouldn't normally expect that for things like alkenes, for instance, because we would be localizing charge in a bad place on a carbon. So if we do this, then we're going to have an unusual looking kind of a structure. There's going to be 4 different things bonded to this carbonyl carbon. So we've got our Y group is still attached, our R group is there. It looks like we're going to have a single bond to the oxygen here. But we know that now our carbon is going to be tetrahedral because we're going to have 4 different things attached. All right, so we've got our negatively charged oxygen that we would predict, and we'd have a new bond to the carbon, from the carbon to the nucleophile. All right, so we'd have something like this. This would be another one of our intermediates. And then we also, in the second step now, would focus on breaking the carbon Y bond. So we're basically taking this proposal and we're inverting the order of operations. So bond forming first and then bond breaking. So we could do this. That would give us an unusual looking structure. We would now just have 3 different bonds to this carbon, so we're probably back to trigonal planar geometry. So we would have the nucleophile still attached. We'd have a positive charge at this carbon, something is just leaving. And our Y group would be lost. So we're not exactly getting to the same products, are we, in this mechanistic step? But there's something I notice. This looks like the minor resonance structure of a carbonyl. If I actually took the lone pairs from this oxygen and put them into a pi bond here, I would have a carbonyl and have this structure here, right? So when we think about this kind of a step, maybe we could write that where the electrons on oxygen are pushing back down to kick out or to force the Y group to leave. Otherwise, we could have written a single red arrow, drawn this, and then think about a resonance structure for this compound, but those are kind of the equivalent concepts. So these are our three mechanistic possibilities. In principle, any of them could happen. And what might be surprising to you is depending on the structure of our acyl compound, any of these three mechanisms has been observed, but one of them is observed almost all of the time. In fact, it's so much more common than the other two mechanisms that, like, we would basically say SNAc reactions in the absence of overwhelming experimental evidence, we assume always have the same mechanism, regardless of the structure of the nucleophile and our acyl group. So we can go through these proposals, and I bet we can figure out which one makes the most sense, which one should be that most common mechanism, just based on what we know about structure and reactivity. So let's look at our first proposal. What we're predicting here is something that's SN2-like. And that tells us a few things. We know that an SN2 reaction requires the nucleophile to come from directly behind where the leaving group is leaving. You might have heard this as backside attack. You probably also heard that this is why we get inversion of stereochemistry in an SN1 mechanism. So what that means is that the nucleophile would have to come from this specific trajectory. But let's actually look at what's going to be true if it comes along that specific trajectory. So we've got a nucleophile with a buildup of negative charge, and it's going to be passing very close to this oxygen, which has lone pairs, which should be very destabilizing. We know electrons repel other electrons. As this nucleophile approaches along the required trajectory for SN2, that repulsion should get intense. And that's going to actually destabilize the structure, otherwise known as a transition state, as you actually start to form the new carbon nucleophile bond and the carbon Y bond breaks. So what we're basically identifying is an issue with strain. You could also think about it as sterics if you wanted, where this angle here is too acute, and so is this one. The nucleophile will interact with both the oxygen and the R group, and that's going to slow this reaction down. So we'll say very slow due to strain. So it's not that this reaction can't happen, it's that this mechanism, if the reaction went through this mechanism, the reaction would kind of almost have to be kind of slow, right? We could look at the second mechanism also. And here we no longer have this required trajectory because we have a carbocation as our electrophile. The nucleophile can approach from the top or the bottom. We don't necessarily have the same kind of real acute approach angles to deal with. But one of the things that we notice is that this carbocation doesn't look very stable. And we know that as we make this carbocation unstable, the rate of something that looks like an SN1 will slow down because the rate of forming this carbocation is what's going to determine the overall rate of the reaction if this is the mechanism. You probably learned this again as, well, tertiary alkyl halides often react via the SN1 mechanism. The logic there is that tertiary carbocations are much more stable than secondary or primary ones. So if there was ever a situation where an SN1 mechanism would make sense, it would be when we can actually access a relatively stabilized intermediate, right? So here we're seeing the reverse. Rather than having a really stable carbocation, we have a really unstable one, and that's going to slow this process down. Very slow due to our unstable carbocation. Let's look at our third example. So here we have no carbocations to worry about, so that issue's out. The nucleophile is actually approaching this carbon not to directly displace the Y group, but to break the CO pi bond. And what that means is that the CO pi bond, and specifically this carbon, is trigonal planar, right? We established that back in the first video of Unit 4. So the nucleophile can come in from like directly above or directly behind this carbon group. And again, we don't have the acute angle problem. We also don't have the unstable carbocation problem. And this intermediate doesn't look awesome necessarily, but we have an O- here. And so like oxygens are relatively stabilized negative charges, even if all I have is the oxygen. So we've got a reasonable intermediate here. And then this second step looks to me like it should be relatively favorable. So we'll clean this up, draw it as a normal carbonyl so that it fits with our arrow pushing, right? We're trading a CO pi bond, which is a fairly strong bond. A CO pi bond is almost as strong as a CO sigma bond for the carbon Y bond. So if this bond were a little bit weaker, for instance, you might expect this to actually be quite favorable to do. And then there's also the added benefit that we're actually ejecting what will normally be a good leaving group for this reaction to work very well. So we've basically decided that we've got serious rate problems with the SN2-like mechanism, we've got serious rate problems with the SN1-like mechanism, and we don't identify the same problems here. So no obvious issues. The mechanism of a reaction is always going to be whatever the fastest means to make the products is. So you could think about it as like these are three different routes that you could drive along to get from point A to point B. But you're typically going to choose the fastest route. Yeah, I mean, this is the whole point of Waze and Google Maps and stuff as far as I can tell. So what we're basically saying is the reaction has a similar logic. In principle, any of these routes could be used, but because this route is most often way faster than the other two, this is the dominant mechanism for a SNAc reaction. So this third option we can call the SNAc mechanism. Right? Remember, it's always a competition between these three possibilities and others also, ones that we haven't talked about. But this third option is so much more likely to happen because it's so much more likely to be the fastest option that we can assume that this is what's happening. Okay. So we sometimes call this an addition-elimination mechanism because of the steps. We call this step an addition because what we're doing is actually adding the nucleophile in exchange for a pi bond, right? When you learned about addition reactions for alkenes, the same thing was happening. You were trading the CC pi bond for new carbon, for like a new sigma bond, for instance. This second step is called an elimination. The idea here is that we're gaining a pi bond between the oxygen and the carbon at the expense of a sigma bond, carbon to Y group. So you'll sometimes hear this called the SNAc or the substitution of acyl mechanism. You'll sometimes hear this called the addition-elimination mechanism. I think biochemists often use that phrase, additional elimination. It doesn't have, well it does, but it's not something that we would cover. It doesn't really have like nicknames like SN1 or SN2. You could call it a SNAc mechanism, that's fine, most people would know what you meant. You could also call it an additional elimination mechanism, most people would know what you meant. The other thing that we can say here is that there's one other piece of nomenclature that's worth knowing, and that is the name of this intermediate. We call this rather than a reasonable intermediate, we call it a tetrahedral intermediate. I bet you can guess why. So what we can say is this addition-elimination mechanism proceeds through a tetrahedral intermediate in the same way that an SN1 mechanism proceeds through a carbocation intermediate. This is the only mechanism for this class that I want you to memorize. So it's really critical that you can, like in your sleep, say, oh yes, addition-elimination, I know what this looks like. I can actually draw out this mechanism for different kinds of structures. I can use these arrows to communicate what's happening from a bond changing perspective. This is such a common reaction. We're going to see so many examples of SNAcs for the rest of the semester, and there are so many in biochemistry that this is really worth having in your head. So in the next section of this video, we'll be doing just that, looking at an example where we apply what we've learned to like write out a mechanism for this addition-elimination reaction. So let's look at the specific reaction where we have a thioester reacting with an alkoxide, so specifically what we call ethoxide, so an ethyl group attached to an O-. So just like we've been doing, what we're going to identify first are reaction roles, so specific atoms that actually serve as nucleophilic sites, electrophilic sites, and then atoms or groups that act as leaving groups. And that will help us to actually orient ourselves to writing a mechanism. Remember, the mechanism is a way of showing how the nucleophilic site and electrophilic site interact with each other. Again, I'm going to look at all of the atoms in here that have electrons that could be donated, likely going to be lone pairs, and I notice that we've got one oxygen here that's carrying a negative charge. So there's going to be a buildup of electron density at this oxygen relative to this one, and certainly relative to the sulfur. That means that this oxygen is likely my nucleophilic site. I know that carbonyl electrophiles are quite common, so I can assign electrophilicity to the carbon of the carbonyl. And then finally, if I know that this is my electrophilic site, I need to decide whether my methyl or my SCH3 is more likely to function as a leaving group. So again, I'll compare anions, carbon minus versus sulfur minus. Which of those sounds better to you? Certainly for me, the large atomic radius of sulfur seems like it should be a good option, and that makes the sulfur group and everything attached to it a reasonable leaving group here. So here's our own leaving group. Cool. So once I've done this, now I have to connect my nucleophilic site using the lone pair to the electrophilic site. So I'm going to draw that arrow, and then I'm going to start thinking to myself, so if I just did this, how many bonds would be on the electrophilic site now? And I would count 5. 1, 2, 3, 4, 5. That ain't going to work. I can't go over the octet rule for the second row elements. So I'm then going to think about, well, either A, what do I know about the mechanism? Could be, I already know it's addition-elimination, or I could look at this and say, okay, if I know for whatever reason I'm not going to be breaking the carbon-sulfur bond directly, because I know that SN2 is unlikely here, the second best bond to break is probably the CO bond of the carbonyl, because I can localize electrons onto a relatively electronegative element, like oxygen. So now I'm done figuring out what's happening, and what's left to do is to draw a structure that conforms to the changes that I've diagrammed with my arrows. We know that these addition reactions are actually reversible steps, so we can get to the tetrahedral intermediate that we'll draw, and that could go backwards. We'll talk about that in just a minute. So right now, the leaving group is still attached, and it looks like I have a new bond from my oxygen that was a nucleophilic site to the carbonyl carbon. That's the dashed bond I'm showing, and then this oxygen is still in the molecule also, carrying now a negative charge. I'm showing one of the two enantiomers of this compound. We know we form both. So our tetrahedral intermediate is racemic. Once I get here, the addition can run backwards. Because if I think about it, I want to reform the CO pi bond, and I have options for how to do that. I could eject a CH3 group. That's one possibility. Probably not too likely because of the instability of a carbon anion. I could eject the sulfur, which I know is what's going to probably give rise to protic formation since I've identified that as the leaving group. Or I could eject the oxygen here. So that literally runs the reaction backwards. So of those options, ejecting sulfur is probably the best, but ejecting oxygen is probably the second best, because this anion is like not great, but it's certainly better than the carbon anion. In the forward direction, the sulfur gets removed. And this elimination step is also reversible. So I'm going to run out of space. I'm going to have to curve around the board here. That's going to reform my carbonyl here. The sulfur carbon bond will break, but the ethoxy group will still be there. Eliminating the sulfur group changes the geometry of this tetrahedral carbon back to trigonal planar, so I no longer have wedges and dashes. And now I've got my sulfur anion as the leaving group after it's left, including the new lone pair. So this reaction could run backwards. We could do an addition, where the sulfur acts like a nucleophile, breaks the CO pi bond, and I'm back to the tetrahedral intermediate. So these SNAc reactions are all equilibrium processes overall, in part because both steps, addition and elimination, are reversible themselves. We're basically going back and forth through this tetrahedral intermediate, and we'll need to decide at some point how to determine or predict, ideally, whether these reactions overall will favor the products or favor the reactants. It's essentially never the case that the reaction will favor formation of the tetrahedral intermediate. This structure is usually a lot less stable than either the reactants or, either the products or the reactants. So in the next section of this video, we'll be looking at a slight wrinkle on a SNAc reaction, and certainly from a mechanistic perspective as well. It's not too bad, but it involves nucleophiles that are neutral rather than anionic. Let's look at a slightly different kind of a SNAc reaction. We'll keep our electrophiles, so our acyl group and something that we're going to call a leaving group. We've been denoting as Y. And we'll change the structure of the nucleophile very slightly. So rather than having a nucleophile that's anionic or carries a negative charge, we'll treat nucleophiles that are what we call protic. So these are compounds that have at least one bond to hydrogen. And for us, this would be like the nucleophilic site would be bonded to a hydrogen. For instance, an OH group or an NH group. The O or the N carries a lone pair that makes the atom nucleophilic, and then there's also this hydrogen attached. We'll look at some specific examples at the end of the video. In this case, we can start using the same kind of logic. So we'll work through a mechanism here. In the absence of any data, we would expect to see an addition-elimination mechanism, so that's a helpful way we can get started. But we also notice that there is a couple of differences in the structures of the final products that we'll have to explain. It looks like this hydrogen is also transferred from the nucleophilic atom to the Y group. So we would need to account for this proton transfer in the mechanism also. To get started, we'll do what we would think of as normal for the SNAc process. We will bond the nucleophilic atom to the carbonyl carbon and break the CO pi bond to make our tetrahedral intermediate. But you'll notice I haven't done anything with this hydrogen yet. I'm still actually, there's not anything I can do just yet in most senses. I'm just going to focus on the nucleophile electrophile chemistry. So that gets us to an intermediate that will look like this. If the nucleophile was neutral and you used the lone pairs into a bond and you still have the hydrogen attached, like so, this nucleophile is now positively charged. Neutral giving electrons will lead to positive. So one possibility is that because this is positively charged, kicking it back out to get here should be fairly favorable, right? Eliminating something or using a leaving group that's positively charged, as you learned about, usually a favorable process. The other thing that can happen is that the Y group can be eliminated also, and both of these things happen to some extent. So kind of most of the time we're going back and forth and back and forth and back and forth, and then every once in a while the Y group gets kicked out. That gives us a new carbonyl. Our nucleophile is still attached to the carbonyl carbon. That proton is still there, and that positive charge is still there. And now we have Y that's got a negative charge on it. It's started out as neutral, and now it's left with a lone pair, right? So we get to this situation. And now what we can notice is we've dealt with all of the structural change except for transferring the hydrogen. And if I think about transferring hydrogens, that sounds like acid-base chemistry. So what we can say is that this proton is probably reasonably acidic because it's attached to a positively charged atom. And we know that the Y group has a buildup of electron density, which is another way of saying that it could function like a base. That means that it would be feasible for our leaving group after it's left to actually remove the proton from the nucleophile. So in this last step, which is acid-base, we get to our neutral substitution product and our protonated leaving group. So we have really introduced this new acid-base step, which is really only relevant when the nucleophile brings in this proton. And neutral, that's important. So protic and neutral. Both of those characteristics have to be satisfied. The reason for that is that once we get here, what we've basically done is we've carried this proton, which may not be that acidic to start, and we've actually acidified it. We've made its pKa go down by virtue of taking electron density away from the nucleophile. We can look at a specific example of this types of SNAc reactions with protic neutral nucleophiles, here with an ester and an amine. So we'll start by assigning roles. We know our nitrogen is probably the least stable, has the least stable set of electrons of all my options. I've got oxygens, those are more electronegative and therefore hold on to their lone pairs more tightly. There's also resonance stabilization of some of the lone pairs in this structure. Good review to see that for yourself. So here's our nucleophilic site. We also notice that it's neutral. The nitrogen atom has no charge. And finally, we notice that there's at least one hydrogen attached to that nucleophilic and neutral site. So all three of these characteristics apply to the nitrogen. We know our carbonyl carbon is likely the electrophilic site, and then if we're noticing a pattern, a lot of times we have these alkyl substituents as part of our carbonyl. It's really going to be the non-alkyl substituent that's going to function as our leaving group. So here is our leaving group. So one of the things I could do, if I didn't need to think through the mechanism, is just predict the products. I don't know whether this reaction is favorable or not yet, so I'm just going to leave these arrows as equilibrium arrows. Who knows? But we know what the product should look like following our general pattern. We're going to replace the oxygen with the nitrogen. The methyl group will stay with the oxygen, and everything on the nitrogen except for one hydrogen will go where the oxygen was. That's the nature of a substitution, right? So I now have something like this. One of the two H's will still be on the N. The other one is going to end up on the oxygen, right? So the Y would be oxygen and then the methyl attached, and then hydrogen is going to go onto the Y group. Okay, so those would be the two structures. To be clear about the protons, I'm going to pick one of these two arbitrarily. There's our proton transfer at the end. And if we were to work through this mechanistically, it'll help you to see this acidity argument that I was making in the earlier section of the video. So let's do a mechanism. So let me redraw these structures real fast. We've already got roles, so we don't have to do that part again. I know that initially I'm likely doing an addition. So I know I'm getting a tetrahedral intermediate. And I'm just going to draw one of the two enantiomers of this tetrahedral intermediate, just to save some time. And I notice that by forming that fourth bond to nitrogen, the nitrogen becomes positively charged. So we know here one of the options is to eliminate what I notice is eventually going to be the leaving group. That would be the methoxy. So here's my elimination. Both of the hydrogens are still on nitrogen. And I've got a CH3 minus here. Sorry, OCH3 minus. And now I'm thinking about acid-base chemistry. So one of the things I could always do is use pKa values to make some decisions about, well, is this a feasible acid-base reaction? And it turns out that these hydrogens are extremely acidic. I know you would be tempted to say that this is an ammonium ion, and therefore the pKa of these protons is 10. But that doesn't take into account this carbonyl. The carbonyl will actually dramatically stabilize lone pairs that you put onto the nitrogen, or another way of saying it would stabilize the conjugate base of this compound. And so the pKa of these protons is around 0. On the other hand, if we actually did the acid-base reaction, that would get us to the products that we've drawn up here, yeah? So here would be my conjugate base, and this would be the conjugate acid coming from the methoxide. Acid base. So what I would need to know is the pKa of the conjugate acid, methanol, this compound here. So this is about 15, it's an alcohol. About 15. And then from those pKa values, I could even estimate the KEQ for this last step. It's going to be 10 to the 15th. So this is highly favorable to remove the proton. Well, we could even compare to what I was saying earlier, that actually using this nitrogen as a nucleophile acidifies these protons by evaluating the pKa of the compound here. The proton in the neutral nucleophile itself has a pKa of around 35. So it's very unlikely, since this is such a weak acid in this state, for the mechanism to start with like removing one of these hydrogens. We would need an extremely strong base for that. Certainly nothing in this compound would suffice. But by virtue of taking this lone pair and using it into a bond and making the nitrogen positively charged, we acidify the protons by 35 orders of magnitude. And not only that, but by virtue of the elimination reaction, we generate a reasonably strong base in methoxide. That allows us to make a prediction that this acid-base step at the last stage of the reaction should be very favorable. So we can see that these neutral protic nucleophiles more or less function just the same as anionic nucleophiles in SNAc reactions. The big difference is the nature of where this proton ends up. It ends up on the leaving group. And also the mechanistic features that we observed where there's an acid-base reaction, almost always a favorable one, at the very end of the mechanism. So you have your traditional addition and elimination steps, along with the tetrahedral intermediate here, and it's just this proton transfer that happens at the end that we have to like incorporate into our understanding. So in the next video in this unit, we'll be looking at real examples of SNAc reactions and starting to do the work to be able to determine which side of this SNAc equilibrium is actually going to be favorable given the structures of the electrophile and nucleophile.